Right, we're going to end this lesson talking more about metamorphic grades and prograde metamorphism. So different regions of pressure and temperature impact the texture and mineral assemblages of rocks in different ways. In other words, you add just a little bit of temperature and pressure, you get low grade rock. Add more and more heat and pressure, you get a high grade metamorphic rock up until the point of melting. Okay? And different index minerals are created. They're most stable in these different temperature pressure zones. Right? So we know that chlorite is a low grade mineral that's going to form first. And then as temperature and pressure increase, you're going to start moving into the micas, eventually getting garnets, maybe ending up in pyroxene or sillimanite. Right? So these index minerals are showing the different grade of the rock. And as we talked about before, prograde metamorphism is what's typical. And even though a rock itself can't retrograde, right? A gneiss can't turn back into a slate, the minerals inside it can start to retrograde. So you could end up with a high grade gneiss with low grade chlorite minerals inside of it if that gneiss was then brought into a low grade environment. So the group of minerals that you have can tell you, well, how much heat and pressure did this rock undergo? And the group of minerals you're going to look at are called mineral assemblages. Right? So it's the group of minerals that are all altered during metamorphism. So you can look at the group, and by looking at the entire group, figure out, oh, how much heat and pressure occurred here. So for example, these index minerals and these mineral assemblages can be applied over a very large region, and you can pinpoint where was the most metamorphism happening, where was, for example, the heart of that subduction zone, that convergence. So this map is showing the northeastern part of the US, and you can see how the different mineral assemblages have been color coordinated to show the grade of metamorphism. So the highest grade metamorphism happened in Massachusetts, and then we got further and further away from that metamorphism, further and further away from the heat and pressure, ending up in Vermont, Maine, places like that. So this brings us to a metamorphic facies, and this is a set of mineral assemblages that indicate a certain range of pressure and temperature conditions. Right? So we take what we see in a single rock and think about, well, what all rocks are there, right? What are all of the different mineral assemblages we see together? So for example, this metamorphic facies has two important consequences. If two rocks of identical bulk composition, so for example, they have the same protolith, they have all of the same atoms in them, have different mineral assemblages, they must have metamorphosed under different conditions. So, right, looking at this image, you can see, well, maybe all of these rocks started as zeolite, so they all started with the same ingredients, but if it underwent contact metamorphism, that zeolite would turn into a hornfels. If it underwent intense pressure, it might have turned into a blue schist, right? Conversely, if two rocks that have been exposed to the same metamorphism have different mineral assemblages within them, they must have started from a different protolith, right? So let's say you find two rocks side by side. Because they're side by side, obviously they've undergone the same processes, they were in the same environment, but they have different minerals inside of them. Well, then you know they started off as two different rocks. Maybe one was a limestone turned to marble, and the other was, say, a shale turned to a hornfels, but both underwent contact metamorphism. Okay. So to give some more examples of this, blue schist and eclogite form under high pressure, low temperature conditions, really common of accretionary prisms. Okay. Green schist, amphibolite, and granulite form under high pressure, high temperature conditions. So think like burial under mountains and volcanic arcs, things like that. And as I said before, hornfels form from contact metamorphism, so low pressure, high temperature conditions. And because of the low pressure, hornfels typically lack foliation. This doesn't mean they lack layering. It just means that that layering is due to the sedimentary layers, not the metamorphic foliation. All right, so to wrap all of this up, here I'm showing you on Earth and all the different tectonic environments where you might find different types of metamorphic rocks. So if we find a metamorphic rock today, we know what type of environment it probably formed in originally.